just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America.
that is willing to
But we're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation,
We need scientists to design new
and
fuels.
focus on net public
We
benefit
need engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those
then
technologies.
we will march towards this.
We need workers to operate assembly lines that hum with high-tech, zero-carbon
We have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Okay, welcome to another episode of Fire Division Podcast. My name is Mark Hinaman, and today we've got Mike Keller. Mike, I didn't warn you ahead of time, but the guests introduce themselves on this podcast. Why don't you go ahead and give us a 30-second introduction?
Yeah, my name is Mike Keller. I'm president of Hybrid Power Technologies. We are developing an innovative approach to advanced nuclear reactors, which we actually own a number of patents on. We're a small company located in Kansas, and we've been working on this for several years. Our approach to the advanced reactors is different than everybody else. What we actually do is we're using a gas-cooled reactor to drive the air compressor of a combustion turbine. The upshot of this approach is, with a combustion turbine, about half the power is used to compress the air. When you use a nuclear reactor, and it's a gas reactor, you double the output of the combustion turbine. So our approach is actually one of the classic economies of scale, which is to increase your output and increase your efficiency. And that's what this technology approach actually does. So with the current advanced combustion turbines, the output of a hybrid is about 1,000 megawatts versus roughly around 400 or 500, just if it was a combustion turbine plant. So the effect of using the advanced reactor to compress the air is significant in terms of what it does to the financials. So that is a brief thumbnail sketch of what we're doing.
Perfect. I can't wait to dig into more of that. Before we do,
our approach is actually based on making a combustion turbine a lot better. With the reactors, honestly, it's kind of long for the ride. So it's just an entirely different approach than all the others.
So, Mike, before we dive into kind of your technology and your guys' business, let's focus on you and kind of where you started. What's your background? How'd you get into this?
I've been in the energy and power business for over 50 years. I actually graduated in 1972 with a science degree in nuclear engineering from the University of Virginia, and went to work at Newport News Shipbuilding and Dry Dock Company working on Navy subs. And that's how I started in the nuclear business. I also have a degree in a master's degree in mechanical engineering. I'm a professional engineer of Kansas, and I've got an MBA. So about half my career was with nuclear power plants, and the last half has been with combustion turbines. So with that kind of background, I was able to come up with this approach of marrying nuclear power and a combustion turbine.
Gotcha. Yeah, that makes sense. When you went to school, were you, let's see, Navy nuke, right?
I was at University of Virginia. They had a nuclear engineering program at the time. And I've always been fascinated with nuclear power ever since I was a kid. So, I'm doing what I want to do. I've always wanted to work with nuclear energy and have.
Yeah, that's awesome.
I have also I've got a senior reactor operator certificate, so I'm familiar with running both nuclear plants, and I've run combustion turbines as well and managed power plants with big combustion turbines on them. So I've got a pretty varied background. I've been all over the world. So, with that kind of experience, you tend to pick up insights that otherwise you might not, if you're just siloed in one particular area.
So hybrid power, you guys are working on the turbine side, perhaps having separate from the nuclear island, or the reactor is just one component. But
Actually,
how'd
we're
you-
working on all of them.
Okay.
Our approach on the reactor is, again, a little bit different than
Sure.
what you might otherwise see. It's actually based on a helium-cooled gas reactor with a graphite core and the triso fuel we're using it, but we're using a block type fuel with pins in it that hold in the nuclear material.
Is it similar to what X Energy would be using?
Nope, not at all. They're actually using the approach where they have balls, small, kind of look like a billiard ball. In the cores consists of thousands of those. This approach is more similar to what the Japanese are doing with their graphite high temperature reactor. But our approach again it's simpler. You know, we looked at the designs that were out there for the high temperature gas reactors, and we felt they were overly complicated. So we have simplified it significantly. You know, my early background, I worked for combustion engineering in the reactor mechanical design department. So I am familiar with reactor cores.
Gotcha. How is yours simpler? You've got some great literature about your technology. I personally appreciate your website. I'm looking at it now. You've got kind of a process flow diagram that simplifies or lays out the system so that someone can interpret it. But why don't you just kind of walk us through it?
Yeah, the reactor, some of the problems you have with a big gas reactor, although the output isn't that much, it is a small reactor. It's around 630 megawatts. But gas reactors are inherently large because they use a graphite moderator. So one of the first problems we ran into was that the size of the reactor vessel, even at 630 megawatts, is large. It's like 25 or 24, 25 feet in diameter. Now, at the pressures you're looking at, the wall thickness would be around 10 inches. I said, well, that's not practical. That's not going to work. So what we ended up doing is we actually employ a vessel inside of a vessel where the high pressure part of it is in a somewhat smaller vessel, but it's made of a different material. It's actually what you call a P91, P92 series, which is commonly used with combustion turbine on the combined cycle plants. And the outer material was classic, what they used with existing pressurized water reactors. So that was one of the first things we had to resolve, because there was no way a vessel that diameter and that thickness, extremely expensive to forge. So what we actually use is a plate, similar to what you do with submarines, actually. So it's
Meaning a plate of metal?
Yeah, you just bend the plate. You don't, and it's not really forged. And the early water reactors, they were actually plate. They weren't forged. The ones they use now, those are forged vessels. You know, the plate's forged versus a rolled plate. So the forging process.
I assume you've got a
expensive.
cap on both ends or one end. Am I thinking about that correctly?
Yeah, the outer vessel has a head on it that's held down with bolts, and then the inner vessel. So the upshot of that is the reactor vessel pressure is only a couple hundred psi, pounds per square inch, versus the 1,000 or so for the inner vessel. But the inner vessel is made of a different material that is significantly stronger.
Gotcha. So I'll try and paint this picture for the audience, because I mean, we're both masters in mechanical engineering, and so it's perhaps easier for us to conceptualize because we've dealt with this stuff. But I mean, you said a plate, and so that's literally just a flat sheet of metal.
Yeah, you roll it.
They've rolled, and you form a cylinder with it that then you'd typically weld, or
you would weld it,
right? And then that acts as your container. Right. And I mean, we in the industry, we say vessel or reactor vessel or pressure vessel, but it's just basically the container that houses the reactor. Right.
Yeah. And there's an inner container that actually holds the core. So you've got there's actually two vessels. The inner vessel is actually to a different part of the ASME code, which we use for pressure vessels. The outer the nuclear pressure vessels, Section 3 in ASME code, they have lower allowables than what you use with a fossil plant, which is actually Section 8. So we're taking advantage of the higher allowables for the inner vessel, basically to make it smaller, and the wall thicknesses to reduce the cost.
I see.
So we tend to approach things from a practical standpoint, and an
Right.
engineering standpoint. It's like, well, how can we pull this off and actually make it cost effective? So you see that approach throughout our technology. We've actually developed a conceptual design for the entire power plant, and that's what, because I've been around a long time, I know a lot of stuff on. I mean, sounds a little arrogant perhaps, but when you've been around the planet for 50 years, you can't help but learn things.
Yep.
So,
Yep. Absolutely. So you've got this design for an entire power plant. I want to continue kind of stepping through your design and what's unique about it, but then kind of dig into the practical side of how we might utilize it. So designing the whole power plant, start with very hot, high temperature gas reactor, use helium
now
to,
that high temperature gas, from a mechanical engineering standpoint, it's tough to deal with.
Yeah.
From the temperatures, relative to a combustion turbine, which is firing at around 3,000 degrees Fahrenheit, the hot gas coming out of the reactor is around, I don't know, 1,400, something like that. I think it's 850 C centigrade, but that's tough to deal with. So again, we approach it from a practical standpoint, and with a combustion turbine, you can use those very high temperatures, but you're cooling the materials. So that's actually what we do with the piping that goes from the reactor to the to the helium turbine that drives the air compressor for the combustion turbine, which is actually located outside of the containment structure.
Right.
So as you march your way through the issues with high temperature gas reactors, we tend to take the approach that's used with combustion turbines, which is cool the stuff off so the materials can handle it.
Gotcha. Yeah. So the nuclear component only acts as about 40% of the plant then.
It's about, energy wise, it's about 40% of it. With natural gas or some kind of fossil fuel, it could actually be hydrogen, the other 60%, and that's actually firing the combustion turbine.
Gotcha. And then you've got a heat exchanger, and walk us through kind of the power block. What's unique about that?
Well, we start at the reactor core, we send the hot gas to the helium turbine. That gas is discharged and sent to a heat exchanger. The cycle is based on what they call a Brayton cycle. It's a gas turbine, a closed gas turbine cycle. Now, with gas turbines, or in this case, a helium turbine at around 800 degrees C inlet, the exhaust temperature is actually fairly hot as well. It's around 900 degrees Fahrenheit. So you have to transport that gas to a heat exchanger, cool it down, and then run it into a helium compressor, which is driven by its own helium turbine to get the pressure back up. You'll start at somewhere around 800 psig, run it through the helium turbine, and its discharge pressure is a couple hundred psig. So with that kind of setup, you have relatively high exhaust temperatures on the turbine that you also have to deal with. Now, one of the things we also noticed is from a practical standpoint, even though it's a 600 megawatt reactor, the helium gas flow is fairly significant. The upshot of that is the pressure losses, especially across the heat exchanger we're using, can be relatively high. So the other thing we did is we split into two turbines, one driving the helium compressor and the other helium turbine driving the air compressor. So that allows us to use piping that you can handle, basically. I mean, that's
meaning
with
piping that's
smaller
sized
pressure losses.
small enough. Yeah.
Yeah, it also allows you to make the heat exchanger something more practical. We are using a compact heat exchanger, but even those can be relatively large with the gas flows involved. So we actually use two different heat exchangers, again, to make the components easier to manufacture. So the upshot is the gas coming out of the two heat exchangers that you've cooled off, you send it to the helium compressor. Now you're cooling off the gas to reduce the power needs of the helium compressor. So we have a single helium compressor with the two inputs from the heat exchangers, compresses it, and then it sends the gas back out to those heat exchangers to be heated back up before it goes into the reactor core, where the gas is heated up even more. So
Gotcha.
it's a classic Brayton cycle in the sense that it's a closed system, so you're is circulating the helium through the system and adding and subtracting heat to make the cycle more efficient. The reactor side efficiency is around 50% with this kind of setup,
Which is pretty good.
Yeah, it's
Some
very
people
good.
may not realize, they're like, wait, 50% efficient, that doesn't sound very good, but when it comes to power and generating power. So does that mean
a typical conventional nuclear plant is it's around 33% efficient.
And not just nuclear power plants, right? Thermal plants.
Well, it depends on the power plant. The efficiency is directly related to the temperatures, the highest temperature. And a conventional nuclear reactor, you're limited on how hot you can get the water.
Right.
And that's how you end up at really low efficiencies. Now, a combined cycle plant, they're around 55% efficiency. But they're also, the firing temperature on a combustion turbine is heading towards 3,000 degrees Fahrenheit. So that's why those types of plants are very efficient, because they operate at much higher temperatures. You can't do that with a water reactor. You can do a gas reactor will get you up there quite a ways. You're not going to get to 3,000 degrees Fahrenheit, but you can get to the point where your reactor side efficiency is around 50%.
So you've got the helium loop that is generating power. How much power does it generate? Or how much heat does it generate, I'll say?
Well, in the context of the overall plant, the air compressor, the decoupled air compressor for the combustion turbine needs about 300 megawatts. So the reactor is providing that 300 megawatts for that air compressor. And with the reactor being around 630 or so megawatts thermal.
Gotcha. And so you're generating about 630 megawatts of heat, and then you're using that to spin a turbine that is on the same shaft as the air compressor?
Well, there's actually two turbines. One is driving the helium compressor. The other turbine is driving the air compressor. Now, one of the things when using helium like this, the characteristics of the gas mean that the helium turbines and helium compressors, they require a lot of blading or stages. So one of the other reasons we split the use of a helium turbine driving a helium compressor and a helium turbine driving the air compressor, the speeds of those turbines are different. In the case of the helium compressor, we're running at much higher RPMs, about 5,000 revolutions per minute versus about 3,000 revolutions per minute for the air compressor, which is a standard sized air compressor for combustion turbine. So the other thing we're doing is we're optimizing the efficiency of our rotating machines depending on its application. Generally, you want the higher you pick up, you increase the speed for the helium turbines and compressors, the fewer number of stages. The upshot of that means it makes it more compact. You know, if you were to, in the past, they tried to combine all the turbines on a single shaft with the compressor. It gets to be too long, and it's very difficult to deal with something like that that's so long. You know, the rotating forces.
Mike, why'd you guys select helium as your power fluid for that?
Well, helium is actually the best gas for a gas reactor. It's inert. In our case, it allows you to have a much lower pressure, what they call a pressure ratio, the difference between the inlet pressure and the outlet pressure. With helium, it's around 2.5 to 3 different, the pressure ratio. If you were to use, say, nitrogen, it'd be around 20. So that would mean your pressures on your reactor would have to be significantly higher. So if you're looking at what's the best gas for a gas reactor, it's helium for a variety of reasons. But fundamentally, you don't have to operate at such high pressures, which makes your wall thicknesses on all your vessels significantly lower. Yeah. And it's also, it doesn't corrode anything. It's inert. So
I heard also it doesn't ionize.
No, it doesn't. It's just basically inert. Nothing, doesn't bother anything.
Yep. Okay, the reactor block. I mean, we've kind of stepped through that, and we'll put a link to your guys' website so folks can go and look at the technical drawing if they want. But the reactor block is one component. Talk to us about the power block or the advanced combined cycle.
Well, the other thing we do before we get to the power block, we actually use a full containment with the reactor. We don't use the approach with other gas reactor outfits where basically if you have a large hole, what they call a loss of coolant, you blow it into the atmosphere. We don't do that. We just keep it confined within a containment. Our thinking on that was, while a containment structure is expensive, all the issues you have to do to try and deal with blowing the reactor coolant, the helium, into the atmosphere, we looked at that and just decided it was a quagmire. Just put a classic containment around it. The containment is actually,
be like concrete dome or
no, it's actually similar? A steel structure. The other thing we do is to take stepping back a little bit on gas-cooled reactors. If the reactor is relatively small, it'll cool itself using natural circulation. In our case, what we actually do is we'll circulate what's ever inside the containment. It moves up through, past the reactor vessel, and goes up. There's a steel shell, and that's actually exchanges heat with the atmosphere. Our containment approach is basically what they use with the Westinghouse API 1000, where they have a containment structure, an outer concrete structure to protect the inner steel shell. And basically the air circulates on the outside through natural convection. It comes in, gets heated up, and then goes out the top of the concrete structure. We do the same thing. So we use the reactor containment to take heat out to the atmosphere, with the reactor vessel sending heat into the inside, circulated by natural circulation on the inside of the containment structure. So the entire system is completely passive. It doesn't require any blowers or anything like that, although we do use them, but that's really more from an operational standpoint. From a safety standpoint, the reactor is passively fail-safe. It's not, and the fuel doesn't melt. This kind of fuel.
Do you guys have like a model or digital model or physical model that shows kind of a mock-up of the system?
We do have drawings that we have.
Sure.
We have, as part of the conceptual design work, We do have various drawings. Some of them are confidential. A lot of this stuff we would ordinarily patent, and we actually have several patents, and one we just got in November. But getting a patent is pricey. So our approach, there's a lot of innovation in this that we would normally just patent, but being a
Right.
small business, we have limited funds.
Sure.
But
So
the
you've
basic
got this.
concept is exact. It's what the Westinghouse folks do with the API 1000, with the internal natural circulation and external natural circulation. So we felt that approach was, given the output of the power plant, which is well over 1,000 megawatts, you can take the financial hit with a more expensive containment. But on the flip side, it's absolutely fail safe, and there would be virtually no problem getting it licensed.
Let's pivot to the business a little bit, if that's okay. So you're working with this design, but where are you in the process of bringing it to fruition? Engage with the NRC, or you need someone to
They're aware of
build one of the
what
power
we're doing.
plants, or?
Well, the fundamental problem we have as a small business is we don't have a lot of money. We've developed a highly innovative technology approach. We patented the technology approach, but we don't get any help from the government at all. And the reason that happens is the way the Department of Energy is set up their financial assistance to the advanced reactors. It involves a cost share. Now, from a small business standpoint, to develop this further, it's obviously tens of millions of dollars, which presumably, as a small business, you'd have to cough up 20% of that. Well, that's out of the question. That's financially lethal to any small business. So one of our biggest struggles is we don't get any help from the government because it would bankrupt us. So the whole thing is, it's irritating, to be quite honest. And I am absolutely certain that there's a lot of innovation out there that just dies on the vane because it doesn't get any help from the government. And I'm speaking directly to small businesses. And that's actually the backbone of innovation in this country, our small businesses and entrepreneurs. So we don't get any help from the federal government. And then we've suggested that they rethink that policy, but they don't listen to us because we're a small business. So it's quite disheartening at times. This actually stems from the 2006 Energy Act, this cost share issue. But if you actually read the act, it says the area of energy, you can waive the cost share. And we've suggested they do that for a general class of small businesses. And we've been met with crickets, basically. So from a broader strategic standpoint, I think the country is being ill-served by the Department of Energy's policies, because I'm absolutely certain that there's innovation out there that could significantly reduce costs and significantly increase safety. But the folks that create that, they don't get any help from the government.
So have you guys taken this to the NRC yet then?
They're aware of it. The licensing process is in itself stupefyingly expensive. I know the guys at
couldn't agree more.
They spent $500 million on licensing.
Yep.
That's an all-in
And
cost.
unnecessarily. Meaning, I would
agree with that.
I don't think it makes it much safer.
It's a far safer
engineers
design,
agree.
and they still have to spend $500 million. It's like, this doesn't, and that's just the tip of the iceberg. All those costs, it washes through the entire design, construction, and operation, and significantly increases those costs as well. You look at the 1000, those guys faced staggering increases in the licensing costs over to what was faced in the 70s and 80s when I worked for combustion engineering. And the AP 1000 is a passively safe design. You just scratch your head and shake your head in stunned disbelief.
Okay, so what's the next step for you guys then?
Well, we're attempting to move the technology forward But on a different front, our latest patent is actually, it applies to combined cycle plants or any power plant that uses high temperature steam. One of the offshoots of developing our technology is we noticed that as you increase the firing temperatures of a combustion turbine, the exhaust temperature gets hotter. Now, with a combined cycle plant, you use that hot exhaust energy to create steam for a steam turbine. But what was happening, and is happening, is the exhaust temperatures, in order to efficiently use to create steam turbines can't handle those kinds of temperatures. They're limited to around 1,000 or so degrees Fahrenheit. A conventional steam turbine. Some of the more advanced ones get a little hotter, but fundamentally you have material problems and you can't really cool a steam turbine. So what we noticed that folks are trying to use a supercritical CO2 cycle to deal with the higher temperatures. And we made the observation that, the supercritical CO2 cycles, they're not really practical when you're dealing with the massive amounts of heat that comes out of a combustion turbine. You've got problems with the turbines, you got problems with the heat exchangers. So what we observed is like, well, instead of trying to use all of that exhaust energy from a combustion turbine for the supercritical cycle, why don't you just use a steam cycle to use the heat that it can actually practically use, and use the supercritical CO2 cycle for the higher temperatures. And that's actually what we were just granted a patent for in November. So we are moving forward to see if we can attract some interest and financial interest to move that technology forward, to then help us move the hybrid nuclear technology forward. We think it's because it has very wide-ranging applications associated with this patent. We think it's very attractive, and we think it will attract the financial interest that's needed to move the technology forward. And we are actually talking with the guys down at Sandia on that very matter. As far as the hybrid's concerned, if we can't get any financial assistance, it's not going to go anywhere. I mean, to be perfectly blunt. So, and there's just no avenue with the Department of Energy there. They're just not helpful at all.
So I'll say it back. You guys have technical expertise, and you've improved or identified a component of the power cycle that is potentially under-designed, and so you've improved it.
The existing combined cycle plants, they're basically plateaued out at the efficiencies they're at right now, because using that steam energy or the exhaust energy, they're running into a ceiling as far as the steam turbines are concerned. What our approach allows you to add several more percent on the efficiency, and that, from a financial standpoint, is significant. In terms of, with the combined cycle plant, your biggest cost is the fuel. So if you can increase the efficiency of your power plant several percent, it makes a big difference on the bottom line.
Definitely.
So
you're trying to take that design and sell it, basically, right? I mean,
that's the idea.
And
license
use
it,
those,
basically.
license it, and
And
use
that's what
those
we
funds
want
to
to
come
get to,
back.
is license it. Now we have incorporated that technology into the hybrid, and we've also have looked at using the hybrid to create hydrogen, but through steam electrolysis, and it's used some hydrogen with the combustion turbine. From a combustion turbine standpoint, practically speaking, you can only use about 30% of the fuel as hydrogen. Hydrogen is a very light gas compared to what you normally use, which is methane. So it's really not practical to run a combustion turbine on nothing but hydrogen. It also requires stupefying amounts of hydrogen. And presumably you would get that from excess renewable energy and generate hydrogen and run the combustion turbine. But when you run the financials on that and look at the practical aspects, it's like, well, that's really not going to work. You can use some hydrogen with a combustion turbine, but you can't run the thing from a practical standpoint with nothing but hydrogen. Physically, you could probably make it work, but
I think it's interesting. We're both engineers, and we've both done the math on this several times. And I mean, other engineers can have different opinions, but we think the challenge of dealing with nuclear is easier than the challenge of hydrogen, which I think says something about
I think
fuel sources. And
I think you're seeing a lot of marketing activities with
Yeah.
hydrogen that are decoupled from reality, to be perfectly blunt.
Definitely, 100%. Well, Mike, we're kind of running out of time here. We'll have to start wrapping up. So, what gives you hope?
Well, I'm tenacious and nothing else. We keep marching along. We're furthering the design. We're putting together a package, a technical package for the concept design. I mean, we have all this information. We're just going to consolidate it into a single document. We're also written a book that's been published, Hybrid Nuclear Energy Systems. It actually goes into all aspects of energy. It is published by the Academic Press, which is part of Elsevier. It's actually a pretty good textbook for anybody because we take a broad look at all energy production and basically rank them, including the hybrid. So it gives a simple explanation of a lot of this stuff, and it will also go into detail at the end of the chapters. It does go into detail. So it's a useful book for those trying to get up to speed on energy production in general and the specifics of energy generation, both from environmental, financial, and technical standpoints. And we also take a look at the licensing of reactors.
Got it. Okay. Well, Mike, I really appreciate the time. Thanks so much for chatting with us.
Okay, well, take care.